Chapter 5 of digital design is about registers transfer level design, which is also called RTL design. So we have seen the combination circuit design, the sequential circuit design. Now we are going one level higher, which is about RTL design. Now comes the read-only memory. This is a RAM as compared to ROM. The memory that can only be read and that cannot be written. So there are no data input lines, so you can see there is no read write input because we can only read. So what is the advantage of ROM over RAM? It is compact, smaller in size, non-volatile. That means even if the power supply is turned off, the data saved in ROM does not disappear. It is faster, especially the RAM. It consumes less power. It does not need power supply to save the bits, so it can extend the battery life. So we can choose ROM over RAM, where the data required doesn't need to be changed every time. For example, a table of Celsius to Fahrenheit conversion in a digital thermometer. So these are the differences of RAM and ROM from the RAM, and the advantages of ROM. ROM is very similar to that of the data cells of ROM are very similar to that of a RAM, except there is no data input. You have a you can see a decoder on which the addresses are given. So these decoder enable the word which needs to be read. So the the ROM cell have word enable and data output cells. So also the data input, which can be written only once. So you can see the block diagram of ROM, in which there is 32-bit data outwards and 10 address pass and enable. So this makes our 1024 cross 32-bit ROM. So there are 1024 addresses, and each address contains 32 bits. So there are very different types of ROM depending upon the storing of data into the ROM methods. So the very first type of ROM is mass programmed ROM, in which bits the data are hardwired as zeros and ones during chip manufacturing. 2-bit word data shown in the figure right has stored 10. That means it has stored 2. Word enable simply passes the hardwire through the transistor. Notice how compact and fast the memory would be. The second type of ROM are fuse-based programmable ROM. In each cell there is a fuse. A special device known as programmer blows the fuse, where we have to blows the fuse using higher than normal voltages. Those cells which can be read as zeros involving some special electrons. Cells which have blown fuse will be read as 1. And cells with the unblown fused are read as 1, and those with blown fuse are read as 0. So this has stored 1 and 0 in the memory. The next ROM type is erasable programmable ROM. The erasable programmable ROM uses the technology of floating gate transistor, in which the gates are floating. So special programmer devices use higher than normal voltage to trap the electrons in the floating gates, where the electrons are trapped using the high voltage. There the input will be 0, and for the floating gates the input will be 1. So for the figure given in the right side, you can see the gate is floating for the left cell, and there are electron trapped in the gates for the right cell. So this is a floating gate. So this is 1 0 stored in the ROM. So to erase this data, we use ultraviolet rays into the chip. So you can see a window on the top of the IC. So ultraviolet rays they can free the charges stored in the gate, and so the ROM can be used again for storing some other data. The next type of ROM is electronically erasable programmable ROM, EEPROM. This is similar to EEPROM. It has floating gate transistors which are electronically programmable. they trap electrons insert in the gates, but over here the erasing is done electronically rather than using ultraviolet erasing done one word at a time. Then comes the flash memory, like EEPROM. All words are can be erased simultaneously. Over here the erasing can be done simultaneously. This flash memory is becoming very common since late 1990s. Both types are in system programmable. Both types of the chips are system programmable. So you can see the EEPROM, we have data input as well as data output. So we have an address, enable, write, and busy pin. So the ROM is used in digital telephone answering machine, where you have to program the answering machine once. What we do is, when you press the record button, the processor gives a command of A to D converter load. So the analog voice is converted to 16-bit digital voice, and that voice is stored in the programmable flash ROM. For example, we are not home. The locations are 0 to 4096. So there will be a write signal, read write address, and there will be a ROM enable. So when you want to listen, play the recording, you will press the play button, and the recording will go from digital to analog converter back to the speaker. So this is used in the memory, where you should store the data without the power supply, because in the RAM, when the power supply is not there, the data inside the RAM is volatile. It get erased, but in ROM it is not erased once the power supply is even shut down. It should be in the system EEPROM or flash ROM, where we can also program the ROM again. Writing to the flash memory is very similar to that of writing to a RAM. The recording is 1, erasing flash is set to 0 to 1 first. The data is erased. Now wait for the flash to finish erasing by waiting of button press when the BU is 0. Then what you do is, you go to the you can write the data into flash memory. Over here the A to D load is 1, A to D buffer is enabled. There is an address at the ROM address. The write signal will be 1 and ROM will be 1. Each time A is incremented, and unless the A is less than 4096, the data is written into the flash memory. The high-level state machine is very similar to the RAM, except there is an erase button also, so you can erase the data from the ROM. So with the evolution of technology, there is a blurring of distinction between ROM and RAM. Why? It has been said that RAM is readable and writable, and ROM is only readable. But some ROMs they can act like RAM. For example, EEPROM and flash ROMs. Essentially, we means that writes are slow, and the number of writes can be limited. For example, few millions time. And RAM can also act like ROM. For example, there are non-volatile RAM. They can save data without the power supply also. The new memory technology evolving the merging of RAM and ROM benefits, and they are it's called MRAM. So bottom line is, a lot of choices available for the designer must find best fit for the design goals. Now the hierarchical approach. In a hierarchical approach, a hierarchy often involves not just grouping items into new items, but also associating higher level behavior with the new items. This is called abstraction. For example, 8-bit adder, its behavior is understandable at high level behavior. It adds two 8-bit numbers, but we can make a 8-bit adder by joining two modules of 4-bit adders. This is hierarchical approach. For example, we can use smaller components to make bigger components. Over here we have a gate example in which we have plenty of 3 inputs AND gate, and we want to make them a 9 input AND gate. So what we do is, we joined the 3 AND gates with the help of another AND gate, so it becomes a 9 input AND gate. Similarly, for example, if we have 4 cross 1 we have 4 cross 1 multiplexer and 2 cross 1 multiplexer, but we want to make an 8 cross 1 multiplexer, so we can join them in a hierarchical approach to make a bigger module. So this is how we want a bigger memory out of small modules. What is over here? We want to make a ROM which is 1024 into 32. That means we have an address bus of 10 bits, with 2 raised power 10 is 1024 and the data bus is 32. So we have smaller ROMs having 1024 cross 8. So what we need to do is we need to join 4 of them in a row and get 8-bit data from each. So we need 4 ROMs over here join in a parallel manner so that we can make a word size of 32 instead of 8. So this is a hierarchical approach. Then we can also join them in one column. For example, if we want to make a 2048 across 8 ROM with the help of 4024 into 8 ROM. In 1024 ROM, we have 10 bits of address bus, and in 2048 ROM we have 11 bits of address. The data bus in both the cases is same, so we don't need to add the ROM in rows. We just need to add them in columns. For this we need a decoder. So the decoder, the most significant address bit will be given to the decoder, and the least significant 9 or 10 address bits will be going to the 1024 ROMs, the one shown in the figure. So the decoder D0 and D1 enables one of the ROM at a time. So when we give an address whose most significant bit is 1, so the lower ROM is enabled and the upper one is disabled. So in this way we can also join small ROMs to make a bigger sized ROM.